Okay, last time we started into Franklin's kite experiment, right? So let's review how far we got on that. Franklin has this idea. He knows that objects, pointed metal objects, can draw electricity off of electrified bodies, right? So he also knows that there's this similarity between these electrical sparks he's been seeing and the noise they make, and lightning, the way it looks, and the noise it makes, thunder. So he has this idea that these thunderclouds are charged up with electricity, and what lightning is a huge electrical spark. Now, if that's true, if he can get a pointed metal object up near these thunderclouds, and there's a conducting path for the electricity to take down to him, he should be able to gather the electricity right off of those thunderclouds. Selah.
You said he had a metal object on the kite, right?
Yeah.
Was it a very big kite so that way it could fly up there?
Oh, I don't know how big a kite he was. I mean, it wasn't a heavy metal object. It was just, what he did was basically just put a long wire on the end of his kite. Okay. So the kite was big enough to handle the weight of the wire, but the weight of the wire wasn't very much. So that's what he... Yes, Ben.
He just, he has a metal piece, and he just, he thinks that if he had a metal piece and you just hold it up, then...
Right. I mean, if he had a long enough, wire, that, I mean, let's say he had a wire that was, hundreds of feet long, and he could keep it straight up in the air, then he wouldn't need the kite at all. Right? Yeah.
Wouldn't it electrocute him?
Well, yeah. If he's holding, this 300-foot wire straight up into this thundercloud, and he's holding on to the end of it, yeah, I mean, if lightning hit the wire, obviously that all the electricity would go right through Franklin. But the way he's going to arrange it, Franklin was fairly careful about this, and he knew the danger. So let me, Selah. Yeah, right. That's what I started to get to at the end of last time. So let me tell you exactly, I'll just draw a picture here of what Franklin did. So we're going to start out with Franklin's kite experiment. And so we have a big thundercloud here. And Franklin is going to fly his kite up to the highest height. There's Franklin's kite, and he's got a metal wire coming out of it. So, metal wire. I'm not much of an artist, so you better label everything in this so you can tell what it is later. Okay, so then here's the kite string, wet kite string. And Then Franklin doesn't want to just stand there holding the string, right? That's not good. So what does he do? He has a shed here where he can stay out of the rain. And he ties a key, metal key, to the end of his kite string. And then he has a silk cord that he holds on to. Here's Franklin. And then he has one other item here. He has let me see. Leyden jar.
Oh. How are you going to test this?
I got it.
Okay, so now you see the setup. So what's going to happen here? Ben?
Probably the lightning hits the kite, or the wire, and it runs down to the key, and the key produces electricity, so then it would go into the Leyden jar.
Yeah, well, no, the key doesn't produce the electricity, right? But it'll conduct the electricity, right? And and if it's electrified enough, what Franklin expects to see is that he'll actually see sparks jumping from the key to the wire poking out of his Leyden jar. Nick?
Wouldn't the Leyden jar blow up?
No, it would only, now if you electrified it enough, I mean this came up the other day, what would happen if you put so much electricity in the Leyden jar? Well, if you put enough in, what you'll see is sparks that actually go through the glass of the jar. In other words, the glass of the jar will break down, and it turns out, at this point people haven't yet discovered this, but later people will prove that there are no perfect insulators, okay? That any insulating substance like glass that doesn't normally conduct electricity, if you have enough electricity, it will conduct even through an insulator. But you need lots and lots. Franklin didn't see that. Now, basically Ben had it right. That's what's going on here, what Ben said, except for a couple of things. One is that Franklin doesn't actually, it's not necessary for lightning to hit his kite. In fact, that would be a bad thing, because it would destroy the kite. So he wouldn't get, that wouldn't be a good experimental result then.
So it would be near enough to have the electricity transferred.
Well, Franklin's idea is that these thunderclouds are electrically charged. Okay, they cause lightning because they're strongly electrified objects, and every once in a while the electricity is so strong that it creates, this huge electrical spark. But what Franklin's trying to do is draw electricity off of this charged object without lightning. In other words, you can, if you, it's just like it's just like the electrical experiments that he's done in the lab in his lab. Now he can, if you have an object that is strongly electrified, some glass tube, say, well, you can hold it close to another object, and if it's strongly electrified enough, you'll see a spark jump. Okay? But you can also just touch a wire to it and draw the electricity off of it, right? So you don't need the spark. So that's exactly Franklin's idea here. He's not actually hoping that lightning strikes his kite. He's just trying to draw a smaller amount of electricity off of this thundercloud. Then,
What if, like, let's say if lightning hit like the wire,
yeah,
would it like?
It would melt it, fry the kite, and the string. It wouldn't. I mean, maybe it would follow this path all the way down here, and blow up his Leyden jar. It wouldn't be a good thing. And in fact, well, there were people who, there was a guy a Russian physicist who heard about Franklin's experiments, tried to repeat them, and was fiddling around with his electrical equipment down here when lightning did hit. He was in the path of the electrical discharge, and he got killed. Enough of the electricity went through him to actually kill him. So, yeah, if lightning hits, I mean, even this Franklin setup wasn't safe. I mean, this is not an experiment I encourage people to do, because if lightning does hit your kite here, I wouldn't be too, I wouldn't feel too safe just because I've got this silk cord here. I mean, well, I don't know whether it'll travel. I mean, obviously, it has a conducting path here, particularly if you've got the key, hooked up to the Leyden jar. But it's a good chance your Leyden jar is going to explode and you're going to get glass in your eyes, even if nothing else happens to you. Yeah.
How did he test it to see if?
Oh, that's the thing. See, here's the outcome of Franklin's experiment. No lightning struck his kite. He is able to draw electricity off of this thundercloud because he sees sparks jumping from his key to the wire of the sticking out of his Leyden jar, and then later he's able to test that his Leyden jar is really charged up with a lot of electricity. He can do his usual experiments, use the Leyden jar to charge other things. Yeah, one way to test would be to grab the outside of the jar while holding the wire, right? But no, Franklin knows, he knows that trick. So he's able to show that his Leyden jar does in fact charge up with electricity. And he also sees other things that indicate that he's getting electricity down his kite string, because he has little frayed pieces of kite string down here that he sees start repelling each other, standing out from from the string. So the little frayed pieces of string start repelling each other, which indicate that there's a lot of electric charge there. Nick?
I've heard that that's why when you spray water from a hose, it kind of spreads out because it's rubbing the hose and it's all charged the same.
Oh, yeah, that might be. There might be something to that. Nick says that he heard that one reason that water sprays out from a hose rather than just coming straight out is because as the water has rubbed against the inside of the hose and traveling down the hose, it has become electrified and then repels the other water.
If you've got nothing on the hose and you just let it run like that, it comes out in a clear, like planes out.
Yeah, I mean, if I don't know how strong that effect is, but it makes sense that there could be at least some effect like Nick's talking about. Ben?
How far was the kite in the sky?
Oh, how long was Franklin's kite string? Actually, I don't know. I know that one other way that people did this kind of experiment was not with a kite at all, but they would take a really tall building in town and just run a wire up it and have a wire, like say if you had a really tall church, you run your wire up your church steeple and stick it up into the air above the church steeple, and then you could gather electricity that way when thunderstorms came over.
Oh, so it doesn't have to be in a cloud because like electricity just travels through the air pretty much?
Yeah, I mean, as long as you've got it high enough, you know, up close to clouds. I mean, if you've got it high enough, you'll gather a significant amount of electricity. Oh, no. There is something special about thunderstorms. Yeah, I mean, I'll tell you more about thunderstorms later in the course, but but this was the first proof that that thunderclouds really were strongly electrically charged, and the obvious implication of that being that lightning is an electrical phenomenon, that lightning is an electrical discharge. Okay? That's what Franklin has proven here. Now that's really important. Now stop and think. Remember back to how electricity started out. You had people rubbing these little pieces of amber and trying to pick up little pieces of straw from, you know, a quarter-inch away, right? That's what they thought the electrical force was, this really weak little attractive force associated with amber. Now, Franklin has shown that the electrical force can be huge. I mean, lightning is electricity. Lightning can knock down trees, destroy houses. Troy?
Does he try and figure out if lightning is a negative or positive charge?
Oh, let me see. He, make sure I get this right, but I'm pretty sure that the thunderclouds are charged negative. Keith, do you know? Okay. So he would, this would be, you know, amber type electricity rather than glass type electricity. I'm not 100% sure of that, though. I'll check up on that. Nick.
They couldn't really confirm whether it was a positive charge or negative charge. They just assumed it was one charge and the other.
Oh, he could have. I don't know whether Franklin did that or not. I don't remember reading about it, but certainly once he has his Leyden jar filled up with the electricity he's gotten from this thundercloud, he could check to see whether or not which kind of electricity it was.
Negative would be on the outside and positive would be on the inside.
In this case, if he had negative running into the jar, he would have positive on the outside of the jar. So, right?
But where would the electricity come from? Because normally if there's positive electricity on the inside, it repels the electricity on the outside. So there will be a negative on the outside.
Yeah, it would just work the opposite way than the case that we talked about yesterday in class. For instance, let's say that that this is, you know, amber type electricity or negative electricity that Franklin gets in his jar. Well, then what would that imply is happening according to Franklin's theory? Well, that would mean that the electrical fluid that was originally in the jar, you know, the normal amount of electrical fluid, has traveled up to the thundercloud, basically, okay, and left a deficiency of electrical fluid in the jar. That would attract the electrical fluid to the outside of the jar. So you end up with the outside of the jar positively charged, right? Okay, so, and he can test. I mean, if he, say, charges up now a piece of amber or something, then he should notice it attracted to the outside of the jar. If he charges up glass, he should notice it repelled from the outside of the jar. Yeah, Troy.
But didn't you say that it would be amber type electricity? So would the amber repel and the glass attract?
Oh, no, what you have, see, in the Leyden jar, you always have a case where whatever electrical charge is on the inside, the opposite, you know, is on the outside, right? Yes, Ben.
So what he's basically trying to say is that large electrical charged objects can, can have large charges.
Yeah, well, that's what he's
charges.
certainly what he's found is that that there are natural processes. I mean, nobody went up and, you know, rubbed this thundercloud, right? I mean, there's natural processes that can generate huge amounts of electricity. I mean, lightning being one here. That you know, thunderclouds just form naturally, but they must form in some such way as to end up with this imbalance of electrical fluid, right? So that they're strongly electrified, and that leads to these huge electrical discharges that we call lightning. Troy?
Was the key in the Leyden jar inside the shed or outside of it?
Oh, it was, I think it was inside with Franklin, I expect.
Okay.
He doesn't, yeah, because he wanted, with his, so he could touch it to his Leyden jar, which was also in.
So we also found out that lightning is negatively charged. It has negative energy.
You know, I believe that's true. I'll double check on that, but I'm pretty sure that thunderclouds are negatively charged. But I'll double check. In which case, yeah, he would have had negative charge in his Leyden jar and positive charge on the outside. Evan.
So he was correct in guessing that amber, when rubbed, has a negative charge and glass has a positive charge?
Oh. Well, actually, that's the way he defined positive and negative. Now, I mean, in a sense, we're going to see later that it would have been better if Franklin had done it the other way around. if he had called amber positive and glass negative. He had a 50-50 chance, and he lost. Because you see, in Franklin's theory, there really is a difference between what he's calling positive and what he's calling negative. He's claiming that there's an actual physical stuff that is flowing, okay, when electricity is transferred between bodies. And the physical stuff that flows, if you have more of that, you're positive. If you have less of it, you're negative. Well, he actually got it backwards. There is a physical stuff that flows and between bodies when charge is transferred from one thing to another. And the actual physical stuff goes, if this physical stuff flows into a body, it actually becomes negative. In other words, the amber has more of that stuff, not less, like Franklin thought. So his convention was the opposite of what it should have been, but he didn't know that, and he, like I said, he recognized that when he called glass positive and amber negative, that was a guess on his part. That he could have just as easily chosen the other way around, and turned out his guess was wrong. But more about the actual physical stuff that flows when electricity moves later in the course. Troy.
So if he had the wine jar and he rubbed a piece of amber
Yeah.
and held it next to it, would it have been a really strong attraction so he could actually feel it with his hand since there's so much electricity?
Oh, probably not so much that he could feel it with his hand. If you hung a small piece, next to the jar, you could see it sway toward the jar a little bit. But these are still fairly small forces, because he hasn't gathered up the kind of electricity that's in a lightning bolt here. He's just taken a little bit of electricity from this thundercloud. Okay. Now, so you all understand what Franklin has proven here? That by proving that these these thunderclouds are electrically charged, the obvious implication is that lightning is an electrical discharge. And he's so at this point, the whole subject of electricity has really changed. First of all, people have a theory of what's going on for the first time. And that theory tells them that this electrical fluid is in all objects, not just in a few. And that electrical forces can be huge, as in the case of lightning. So all of a sudden, this whole subject has taken on a whole new importance in science that it didn't have before Franklin. Okay, now Franklin made one more interesting discovery that I want to tell you about. It's a discovery that surprised him, that he didn't expect to see this. What he did was he took a metal cup. Okay, so you
what was this experiment called?
What is this experiment called? All right. Metal cup experiment. So you have this metal cup. And let's say that you charge up a Leyden jar, and you hold you touch the wire to the inside of this cup. Okay, so you're giving some of your charge that you've built up in your Leyden jar, you transfer to the cup. Okay, so you're just charging this cup up. And you actually charge it up touching the inside of the cup. Okay, so you're putting this charge, trying to put the charge on the inside of the cup. Then, okay, after you charge this cup up, you test whether or not you can just to see whether it's charged up strongly. You take a little piece of cork. This is what Franklin did. He had in effect a little tiny fishing pole, and he had a silk cord hanging down attached to a little piece of cork, and the cork's light, and so if you hold it up to a charged body, the cork close to the charged body, what's going to happen? It's going to move toward the charged body, right? It's just going to attract, same way amber attracts a piece of straw. Okay, this is just the old effect that Thales discovered. So Franklin holds his little piece of cork next to the outside, and sure enough, it starts swinging to the outside of the cup. Then he puts the cork inside the cup. Okay, so so now he's got the cork hanging down inside the cup, say close to one inside wall. And what does he see then?
He sees the cork repel.
Repel instead of attract.
Yeah.
Okay, why would it do that? Now remember, the cork isn't charged. He hasn't.
Never mind.
He didn't touch the cork to the outside of the jar. The cork is just neutral.
Oh,
Nick.
It wouldn't do anything?
Yeah, that's exactly what he sees. But that's a surprising result.
Because all sides are pulling on it?
Oh. Well, that actually is part of the answer. That's very good. But this surprised Franklin because he figured that, he charged up this cup and he assumed that the charge would be everywhere on the metal surface, inside and outside. And he knows that if you hang this light, non-electrified body next to an electrified body, that you'll see an attraction. Okay, so he expected that the cork would be attracted to the inside walls just like it was attracted to the outside. But that's not at all what he saw. What he saw is it's attracted to the outside, he puts it inside, and it just hangs there. It's not attracted to the inside walls at all.
Wouldn't it be like, even though there's a stronger attraction on the side that it's close to, on the other side there's more of an attraction even though it's less strong, so it would just not move?
Oh, okay. So you think that the reason here is that it's attracted to this wall, but it's also attracted to this other wall, and that's canceling out.
Well, like it's attracted to like this surface, but each side.
Yeah. Well, there is something like that going on. That's right. And now, but you would not see that kind of argument. You would think is you would expect that to apply certainly if you hung the cork right in the middle, right? Because then you would think, well, there's equal charges all around it, so it has no reason to go one way versus the other. So obviously it won't move if you hang it in the middle. But what Franklin found that surprised him was no matter where he put it in here, it wouldn't move. Neat.
But isn't if you put it to the side, there's more space pulling on it from the other side?
Yeah, that's exactly. I mean, does that remind you of anything that we learned last year, Nick?
I don't remember what it's called, but if you go anywhere in the earth or something, the gravitational pull cancels out.
Right, right. If you hollowed out the Earth, okay, so the Earth became just this spherical shell of mass, okay, then those of you that were in last year's class remember that Newton showed that in that case, no matter where you were inside this hollowed out Earth, there wouldn't be any gravitational force at all. That it would that all the mass that pulled you in one direction would be exactly counterbalanced by the mass pulling you in the other direction, and that's exactly what is going part of what is going on here. So now Newton showed that only worked for gravitation if the gravitational force was of a certain character, right? Do you remember what the key, Evan?
It falls off as the square of the distance.
Exactly. Okay, so that Newton showed that for gravity anyway, this kind of effect only works if the force varies inversely with the square of the distance, which he showed, of course, gravity does. Okay, so the gravitational force you'll remember is gravitational force between any two masses is just, the gravitational constant g multiplied by the product of the two masses and divided by the distance between the two masses squared. And just to review, if you have, a big shell of mass, and let's say you put a little mass, like not in the center, but off to the side, like right here. Well, the mass over here will pull that little mass toward it, right? But the mass, all this mass over here, will pull it in the opposite direction. And Newton showed that these forces that pull it in different directions exactly balance one another if gravity falls off as the square of the distance. It's the inverse square of the distance. Okay, so what Franklin is seeing here is that if you have charges all around this, this mass distributed on a conductor, that inside you don't seem to get any electrical forces at all, and that actually, now Franklin didn't know what to make of this. I'll get to you in a minute, Troy, but actually let me tell you what Franklin said about this experiment. Said the cork was not attracted to the inside of the can as it was to the outside. And though it touched the bottom, yet when drawn out, it was found not to be electrified by that touch, as it was by touching the outside. Now this fact is surprising. He's writing to a friend of his. He says, "You require the reason. I do not know it. I find a frank acknowledgement of one's ignorance is not only the easiest way to get rid of a difficulty, but the likeliest way to obtain information." So Franklin admits that he doesn't quite know what's going on here. That's, by the way, another mark of a great scientist. You know, he doesn't pretend to know when he doesn't know. He fesses up to his ignorance. So now notice Franklin just told you the other remarkable result of this experiment. Not only does he not sense any electrical force inside the cup, even when he touches the inside of the cup with the cork doesn't become electrified. So there's not even any electricity on the inside surface of this cup. Very peculiar. Yeah,
Is
Daniel.
that because when it touches, it's so close that the electricity can bounce off from it to the other side, or?
Well, no. Franklin had an idea of why there wouldn't be electricity on the inside part of the cup. I mean, he was thinking in terms of his theory. Now, if you think about Franklin's theory, can you think of any reason why all the electricity might run to the outside of the cup? Sure.
Since it's repelling. Like,
Yeah, that's exactly what Franklin thought was, well, let's say I've put an excess amount of electrical fluid on this cup. Well, electrical fluid repels other electrical fluid. So I should expect that excess electrical fluid to try and get as far away from the other electrical fluid as it can. The way it can get maximum distance away from the other electrical fluid is for all of it to run to the outside of the cup. Neve.
Did you try giving the cup a negative charge and seeing what would happen?
Oh, yeah. Actually, it doesn't matter. You get the same results whether you make it negative or positive. Yes.
What happens
Nick.
if you put something really brittle inside? Just like between two charged things, would it like rip it apart?
Oh, if you put something like fragile or breakable between two highly charged, yeah, I mean, if you have, say, two highly charged plates, and they're so charged up that sparks can go between them, strong sparks, I mean, that could cause damage to whatever material is between them. It'd be like something being hit by lightning. Troy.
Does the shape of the, if the cup was in a crescent shape, would it still work that way?
Well, actually, it works the best the smaller this hole is and the more enclosed the cup is surrounded by metal. And in fact, the class is actually, I'm through my time right now, but I'll tell you one thing. To test, I'll say more about this next time, but to test this result, a later scientist is actually going to have a big metal container that he charges up really strongly and then just walks inside. And because he trusted this result. And
Was he smart to it?
And he was smart because, sure enough, he didn't get shocked at all. There were no electrical forces inside his metal container at all, even though the outside of it was really strongly charged.